Hello and welcome back. I think this is the third video on my YouTube channel, and in this video I will talk to you about the reinforcement learning with verifiable rewards. So as you know, I have been building this open post training system for reasoning models, and one of the first things I wanted to understand was GRPO and the RLVR training. So in this video I ran some experiments on my Qwen3-0.6B parameter model. That's the base instruction tune model, and I implemented the training pipeline. And in this video I will walk you through some of the interesting challenges I faced and maybe some interesting findings here, because I evaluated my model on the same Math 500 dataset, and I will walk you through this video. So stick with me maybe for next 20 minutes. This video is not going to be long, maybe 1 hour or 2 hours long, so stick with me. So first I want to make it clear, the goal of this project wasn't to train a state-of-the-art reasoning model, but the simple goal was it was a simple goal to understand the end-to-end post-training pipeline, like the reward computation, the GRPO optimization, like the evaluation, and some of the engineering challenge that I faced in this experiment. This is like a small experiment. There's not a big scale. I was using the Lightning AI Studio for my GPU. And first, let me give some a little intro to RLVR. Actually, the reinforcement learning with verifiable rewards is something first I want to make it clear, do you know when the ChatGPT came and there was this famous pipeline you might have heard about, the reinforcement learning from human feedback, RLHF pipeline, where we have this separate reward model and we have to train the separate reward model, and that was a lot of big complex task actually, where you have to take this data and train the reward model and later on guide the policy, your large language model, and improve it on the preferences and do the preference tuning. But then maybe in 2024, if I'm not wrong, the Allen Institute of AI, they came up with this TU-3 paper, TU-3 paper, and where they introduced this concept of reinforcement learning from verifiable rewards. So it means instead of using that learner reward model, we have automatic verifier. So what is this automatic verifier? It's like when the LLM is generating a response, there is this verifier. Maybe like this Python function here, the reward RLVR. So this will be our verifier, okay? And this will give reward to our generated output. If I'm asking a model to maybe do the multiplication, the simple multiplication 10 cross 3 or maybe 10 into 3, and the LLM will give me some response, and if it got the correct answer I will give it a reward of 1, otherwise it will be 0. Okay, so I hope the RLVR pipeline, and I'm not going deep inside this, so maybe I might later come up with a video, but for now I'm literally busy on other things. So I just want to make this video a short 20-minute video, and that's it. Yeah, so now a little bit about the GRPO algorithm. GRPO was inspired from proximal policy optimization, where we have this critique network, the value network with us. But when the GRPO it first came into, maybe it came in 2024, maybe late 2024, and the purpose of this GRPO algorithm was if I'm giving any prompt to LLM, it will generate multiple responses for the same question, and then we will compute rewards as we did in the proximal policy optimization algorithm, but for all the responses. Okay, and then what will happen, as we will give rewards to the responses, then we will be optimizing model, the large language model, to increase the probability of responses that perform better than the group average. What is the group average? Let me show you this piece of code here, I guess. Let's see, these are the 4 rollouts the model generated. This is like an example, and for the first 2 it got correct answers, and for the last 2 it got 0, the 0 reward 0. Okay, and for first 2 it is 1.0, and then we are converting it into tensor. And here is the advantage. What does advantage tell us? It tells us which rollout in these 4 responses is performing better than the group average. Group average means reward is not mean. Okay, and please don't ignore this rewards dot standard deviation. This is just for the normalization purposes. Okay, so purpose here is to increase the probability of the responses that perform better than the group average, and then at the same time we will be decreasing the probability of the responses that perform worse. Like we'll be decreasing the probability of these two responses because we got a reward of 0.0 for these, and we got reward of 1.0 for these corrected two answers. I mean corrected two rollouts. So in the GRPO terminology we call it the rollouts. I mean the RLVR pipeline, we call it the rollouts. The multiple responses may be 4 or 8. Okay, so I'm not going to like spend more time here. I think I explained these type of things maybe in my previous videos also. So let's get to our setup actually. It's training loop. Okay, so it's been like maybe 10 or 15 days since I ran this experiment, and now I'm making a video because I was literally busy on my research work and I have to read a lot of literature for my research. And yeah, so the research is actually a heavy task and it takes time for research to get mature. So I want to talk about the setup here actually. So as you know, in my previous videos, I'm running my experiments on the same Qwen3-0.6 billion parameter model where I have my own architecture and I have downloaded the weights from Hugging Face. And this is the base instruction tune model from the Qwen. And for this experiment, I will be using, let me go here. I think I was using the Tesla 4 GPU here. Yeah. And let me talk a little bit about this training loop. Yeah, so here I have like let me go here. Okay, so inside the train GRPO, when I ran my first algorithm, I mean the first RLVR-GRPO training run, and I was giving some inputs to this function like num rollouts equals 4 and the max new tokens was at 300. Okay, so it means the model will generate 4 responses, different type of responses, and then we will have this automatic verifiable like the reward RLVR function that I showed to you earlier. And the hardware was Tesla 4 GPU and I was using the Lightning AI Studio, and you can see the learning rate and a lot of other things as well, and the max token was 300. And the two parameters that are literally most important here to look at, maybe 3, including the learning rate, is at 5th scale, fifth factor, and that is 0.00001, I guess, at 5th. Yeah, and we have our max tokens equals 300 because I'm not going to increase it, man. Maybe like it will exhaust a lot of compute costs. For every rollout it might go later maybe till 1000 or maybe 2000 sometimes. So I want to like shrink this, and I will be running it for 50 steps. So when I did my first experiment here, and I have this checkpoint saved here, every 5 steps it will save a checkpoint, the model, and then we will save it. And sometimes like the training loop was literally interrupted because of my CUDA was out of memory because I was using the Tesla 4 GPU here. And then I took this checkpoint, the setup 00005 checkpoint, the 5th steps checkpoint, and I evaluated model on this, and I will be like happy to share the results with you. So for our first time, I was maybe loading this. Yeah, I loaded this checkpoint, and I think for initially when I was running this notebook, I tested with the base model like how good accuracy my base model was giving. So base model here is a instruction tune model, the same instruction tune model that we used previously. And I think I made a mistake in my previous videos because there was this thing, instruction tune model. Yeah, so there was this thing in my tokenizer that I have to activate my chat template responses at a generation, the add generation prompt. I think there was some name associated with it. Let me check it from. Yeah, here it is. Yeah, I had to activate these two things, apply chat template and add generation prompt, and otherwise the model will like give some random garbage, and it wasn't literally stopping when it was encountering the end of sequence token. So I later on figured this. So there was this mistake in the previous video. So it's not a big deal actually. This is a small experiment we are doing with it. And I later on found this cause my model wasn't like stopping at it wasn't encountering the US token ID. So I thought like, why not to debug this, and then I found this problem. Okay, so when I was first running this notebook, I experimented with the base model, and I ran the evaluation function on 50 problems from the math test dataset that we used in the previous notebooks also, in the previous videos also. And you can see like out of 50 problems, the model accurately gave us 32 correct answers out of 50. Okay, so it means we got a 64% accuracy, and the time it took was 7.8 minutes, and the average response length was 303 tokens. Okay, and then when I loaded this checkpoint with the same function, so don't get confused here. I first executed with the same base model that we used in previously, and then I have to change a little bit of my code in my model and load model and tokenizer function, and then I downloaded this checkpoint, the fifth setup checkpoint that we got from here. Yeah, and let me show you the results that I got from here. So when I ran the same math dataset, the 50 problems of dataset on this checkpoint, the 5-step checkpoint, I got the accuracy of 48%. It means we got 24 problems correct out of 50, and the total time it took was 5.9 minutes, and then the average response length was 223. So it means there is some change, like the model, the GRPO training run, the RLVR-GRPO training run is performing literally bad on 5th steps, cause when you are starting your training run early on, the model might like perform really bad than your base model. And the average response length was, it was taking at least 303 tokens for the base model, but I can see the decrease in the average response length. Yeah, during evaluation, yeah. So it's 223. So there's a lot of drop on average response length. It only took 203 tokens in the average to come up with a solution. And then, as the model was literally performing bad, I will share the summary at the end of this notebook. I have this here. Yeah. So as the model was performing literally bad on my second test, where is it? Yeah, it was performing really bad because of only 5 steps of training. So I thought like, why not to test it again? And this time I changed my Tesla 4 GPU because it was running out of memory. And this time I made another change. Instead of 4 rollouts, I'm now generating 8 rollouts. I'm asking the model to generate 8 type of different responses. That's called the rollouts in the RLVR pipeline. And the max tokens will be again 300. Okay. And this time we ran the training for maybe 50 steps. Yeah, we got 50-step checkpoint here, and then I loaded this checkpoint, the 50-step checkpoint. Yeah, and I had to change a little bit in the tokenizer and model and tokenizer function, and then I downloaded. So don't get confused about this. This is the rendering from the Lightning AI Studio, and I downloaded this notebook. Yeah, and this is the 50-step GRPO checkpoint. And now let's look at the results on the same math test dataset. Okay, and I ran the evaluation function again, the evaluate math 500 stream function, and this time the model performed a little better than the previous checkpoint, the checkpoint where we ran RLVR training for 5 steps, and this time we ran training for maybe 50 steps, and you can see the increase in the accuracy. Like this time the model at least got 30 problems correct out of 50, but still there is a catch, and you can see like the time it took is 3.9 minutes. And there is this thing, the model is like, it is going down and down. It means that The model is preferring the short reasoning traces, and it is solving the problem in just less tokens as the training is going forward. Like initially when I ran this checkpoint, where it is, yeah, this is the evaluation code, I'm sorry, but you can see the model is at least taking 223 tokens to in average to come up with a solution. And after we trained it for 50 steps, so it is decreased to 19. And still this checkpoint is not better than our base instruction tuned model, because we only ran this for 50 steps. So I might have gone for 500 steps or maybe 1000 steps, but I was running out of GPU and I didn't had the lightning AI credits. I wasted them, or maybe I spent them on other things, other experiments, small experiments. Yeah, not wasted, but I experimented. Yeah. So the notes I got from this experiment was, it is all listed here, the evaluation results. Okay, so the base model got us 32 problems correct out of 50, and the accuracy was 64, and it took us almost around 7.8 minutes at average response length of 303 tokens. And then came the GRPO run. So GRPO run was the 5-step RLVR-GRPO run was trained for 5 steps, and max rollouts was 4, and the max generation length was, the max token length was 400. And you get this sparse binary reward. That means this is a binary sparse reward. That means if you got the math problem correct, and you will give the reward of 1, otherwise it will be 0. And the evaluations we got for this checkpoint was, we got 24 problems correct out of 50, and accuracy 48%, as I showed this to you. And this time the time was reduced from 7.8 minutes to 5.9 minutes. So it means after 5 steps of training of RLVR-GRPO training, the model is preferring to generate small reasoning traces and solve the problem in just less tokens. Okay, and then for the 50-step RLVR-GRPO checkpoint, we got the rollouts of 8, because we wanted model to generate 8 type of rollouts, and the max generation was still 300, and this was binary reward. Same setup was same again, only the rollouts changed from 4 to 8, and the evaluation results we got was 60% this time, but it's still not perfect as the base instruction tool model, but we have learned a lot of things. What does that mean? What kind of findings I found from here? So I have listed them here also, and you can see the time decreased from 5.9 minutes here to 3.9 minutes. Okay, you can see this. Yeah, I got the touch screen computer, and the average response length is 219 tokens. Yeah, maybe almost same. And the observations. Okay, so the 5-step RLVR-GRPO checkpoint underperformed the base model, dropping accuracy from 64% to 48%. So that is the finding. And the 50-step RLVR-GRPO checkpoint recovered much of the lost performance, improving from 48% here. The 55-step GRPO run, RLVR-GRPO run, that gave us 48, and the 50-step run gave us 60% accuracy. That means there's a lot of improvement in the performance. Okay, and then I have written it like the final RLVR-GRPO. I have to read this again because it's been so many days since I started this notebook. The final RLVR-GRPO checkpoint remained slightly below the base model, because our base model was giving us the 64% accuracy, and our 50-step RLVR-GRPO training run gave us 60% accuracy. Okay, so it means the 50-step checkpoint is still underperforming the base instruction tool model, and the difference compounds that to only 2 questions on the 50-step problem evaluation side. So it means it just got only 28%, only 30 problems correct out of 50 problems, whereas our base instruction tool model got 32 problems correct out of 50 problems, and that's the difference of 2 questions. Okay, yeah. Then the response length, this is the main thing what I want to focus here. focus here on the response length decreases substantially after RL training. It means the model is preferring the smaller trajectories now, and it's from 303 tokens to 220 tokens, and we are getting a lot of benefit. And it's because maybe the rollout size was 8, right? Yeah, not much difference, but between the 50 step checkpoint and the 50 step checkpoint, but there's a lot of difference between the base instruction tune model and the 50 step GRPO training run. Okay, so it means suggesting that the policy learner shorter solution trajectories. And evaluation latency also decreased as response lengths became shorter. It means the same, like you can see the average response length is decreasing from maybe 223, maybe here it took 303 tokens, then 223 tokens, then 219 tokens. So it is decreasing also, and that's a really great finding. Yeah. And then training used a sparse reward signal based only on a final answer correctness, providing limited learning signal compared to the tensor format. Okay, so it means we are we have this binary reward function, the reward RLVR function. I will show that to you again. And then the last one was these results suggest that the GRPO implementation is functioning correctly and the learning occurred during training. However, additional training steps, not the evaluation sets and improvement needed to determine. Okay, so what I have written here is from the ChatGPT. Actually, I wrote a little bit and then I asked ChatGPT to frame this. And it's been so many days I have to read this again. I'm sorry for that. But it means like what I found from this experiment was like if I can like run this model maybe for 500 steps or maybe 1000 steps, it might later on outperform the base instruction tune model, and it might later on at 500 step it might later on outperform your reasoning base instruction tune reasoning model that you got. It's not the base instruction tune model, it is the reasoning model where we adjust the thinking tags, as I told you in my previous videos. Like Qwen3 has this, Qwen3-0 model has this capability where you just enable the thinking tags via your tokenizer, and that's what I was saying, showing to you in the lower model and tokenizer function, where you keep that add thinking tags equals true, and your base instruction tuner model will automatically become the reasoning model. So what I mean here, after maybe 500 step training, the RLVR-GRPO training, it might outperform the 500 GRPO step checkpoint, might outperform your base instruction tune model and the base reasoning model you got already from the Qwen, the downloaded model. Okay, so you have to just enable those thinking tags. But I think I didn't run it for 500 steps. Maybe I will do a new experiment here and maybe run it for maybe 1000 steps or 700 steps and later on evaluate again. So I hope you got a lot of idea from this video, and there's a lot to learn again from here. So let me go back a little bit and give some intuition about the reward function. Excuse me. Okay, you have this reward RLVR. So this will be your verifier. Okay, so it is just taking two things: the generator answer, the generator rollout from the model, and your ground truth, and it will call your extract final candidate, and it will like extract that final boxed answer, and then it will compare with the ground truth. If that was correct, it will give you a reward of 1, otherwise it will be 0. And this is a great function that is giving the reward. And you can see like here we got the answer of, we had the rollout. This is actually example rollout here. Yeah, it's not generated from model, but I have written this. I got this from the Sebastian Rashka's notebook. Yeah, so check him. I'm learning a lot of things from him also. And you can see like, yeah, your boxed answer is the log probability. I'm sorry, I have to go here. Okay, and first you got boxed 83. It means you will get the reward of 1.0, and here you got boxer 83 again. It means it will give you will get a reward of 1.0 again. And then you are the final answer is 83, but it is not inside a box. It's clearly written here. If not extracted, it means you will get return of 0.0. It means you will get 0.0 as reward. And we get boxer 38. That means this is not a correct answer because I am passing 83 here as a ground truth, and you will get this rollout as false. It means you will get a reward of 0.0. So that's how it's happening, and rest of the core maybe look more similar to proximal policy optimization. And inside the proximal policy optimization, we only get one reward. I mean only one rollout from the model, but here the GRPO has power, while you will get multiple responses from the model, and then you will calculate the rewards, the advantages, and later on it will guide your policy, the large language model, and you will optimize depends on your problem, the KPI you have. Like the GRPO and RLVR are famously used for the math and coding tasks and for solving these complex scientific problems. And I think this is the greatest innovation in the post-training recipe, in the post-training field, and RLVR-GRPO is one of my favorite recipes of doing making your base models, the reasoning models actually. So I hope you got a lot of intuition here. This was not a big video, but at least you have learned how to maybe navigate things and how to maybe run some experiments. So I hope this is enough for this video, and I will meet you in my next video, and have a great life.